So today we're going to talk about more the physics aspect of the phase field crystal modeling, especially the solid property of the phase field crystal, right? So there you can see dislocation, grain boundary, and how the dislocation interact and get annihilated, for example. But before that, I would like to talk a little bit more again about the relation between the classical density functional theory of freezing and the phase field crystal model. And this part, basically, I will quickly go through Professor Elder's paper in 2007, which is very important. He shows a way that I can start with the classical density functional theory and how to formulate a corresponding phase field crystal model, okay? And after that, I will talk about the linear elasticity in phase field crystal model, which means if we start with this phenomenological free energy functional, why would one expect the linear elasticity coming out of the free energy or from this equation of motion? And whether to certain limit, whether the mechanical equilibrium is obeyed or followed by the phase field crystal model, right? So those two parts are fundamentals for solid property, right? Once you have those properties being captured, then if there is a dislocation occurring in your system, like defects or dislocations, then you know the strain field is going to relax properly according to the linear elasticity. So even there, we can compare the strain field from the classical elasticity theory and with the PFC. Okay, and of course you can have an array of dislocations, right, like this. So that will form a grain boundary between two nearby grain. So there we can even calculate what's the grain boundary energy in the PFC and whether that follows also the classical prediction, which is the Ricciardi law, okay? Okay, so first thing first, let's talk about, once again, the classical density functional theory of freezing and the PFC, right? So you can refer to more details from this Ken Elder's paper published in 2007. As we just described last week, the classical density functional theory would have those two terms. One is from the ideal gas term, and the other is from the interaction. Okay, so you have this pair correlation function, which means if the density is small enough, we don't have to worry about a higher order correlation because those are proportional to the delta rho cube and force power, etc. And this ideal part, you have some structure like rho log rho minus rho, right? So something we talked about before. So I think you are sort of familiar with it already. So basically, if that free energy difference is relative to the liquid state, but you can also expand again that free energy difference to some arbitrary reference density, let's say the rho bar. So just do a straightforward expansion, and you can redefine a dimensionless density, right? It's rho minus rho bar and divide by the rho bar. And with a little bit of algebra, you are ending up with this free energy functional. So you still capture the main feature that you have a density correlation term, right? You see this n times rho times n of r prime. And other terms are just simply expand from this log term, rho log rho term, right? So you are expecting a infinite series of polynomial of n right here. Okay, so everything starts from the classical density functional theory, and after the expansion, we end up with this simplified or truncated free energy. So what Professor Elder did is basically saying that now since we retain this correlation function, then in the reciprocal space, that's a typical liquid structure factor will look like, right, near the melting point. So instead of just fitting the peak, the property of the peak, you can actually fit more parameters to the pair correlation function. So this is the correlation function in the reciprocal space, C of k. And if you want to capture more feature, you can, of course, fitting the curvature and the height of the first peak. But you can also fit the C naught, which is when k equal to 0, C of k has certain value, right? So in this paper, basically they fit the correlation function in the reciprocal space with this quartic polynomial. All right, and there is a certain constraint of the sign of those three C0. C0, C2, and C4 are three numbers, and since at k equal to 0, the structure factor would have a negative C0, so C0 has to be negative. But when k increases, you start to see an increase in this function, so which means C2 has to be positive. And of course, we only model the first peak, and this function goes down at larger k, so you will need the C4 to be something negative. All right, so the simplest fitting basically only deal with three parameters, right? And if you know that's the reciprocal description for the correlation function, the corresponding real space representation will be something like this, right? You have a lot of Laplacian operation, and which we have seen that in the phase field crystal model. So once you plug it in here, you start to pick up like minus k squared and minus k squared, or the minus k squared, the whole thing squared, right? That will give you the k to the fourth power. Okay. So before we move on, I think there is a lesson here, or basically people have been doing, is that instead of only fitting the first peak, if you have the whole information from MD, like doing the correlation function, you can actually just direct plug in the whole shape of C of k and doing the evolution equation in the reciprocal space. And when you want to calculate the free energy, right, there is a simple relation between this integral, like n rho c times n the double integral. It's just a very simple Fourier sum of something, right? So if you want to see what's the effect from maybe the second peak, a third peak, etc., or the shape of EC of k, something you can extend this method straightforwardly is just to incorporate the shape of C of k directly and see how those addition into your free energy will change the property of your solid-liquid interface. Okay, but here we just focus our discussion on this C of k, which we just fit with the first peak and then also the C0. So three parameter fitting, right, is used in this 2007 paper. But there's some physical meaning of those three numbers, C0, C2, and C4. For example, we know this 1 minus rho bar C, if we take the k equal to 0 mode, right? So in Fourier space, 1 minus rho bar C0, these things basically corresponding to the bulk modulus of liquid. So which means if you compress your liquid, you're expecting the energy coming higher and higher, right? So something you can really see straightforwardly from the free energy functional. Now consider the density, they are homogeneous, right? So if there is a density change, so you can change the density by squeezing or expanding the volume, then you are seeing that the energy increase proportional to this rho bar kBt times some coefficient, right? This 1/2 times 1 minus rho c. But there's something corresponding to the volume strength square. So straightforwardly, you immediately see that 1 minus rho C0 corresponding to the liquid elasticity. Basically, it's the bulk modulus, okay? So proportional to, but if you want to get the older dimension, right, there's like rho bar kBt on the right-hand side, all right? And some other derivation could evolve by taking the derivative of the Helmholtz free energy with respect to the volume. So if that's homogeneous, so V is over here, right? So you divide the volume to the left-hand side, you are ending with the pressure, and pressure take a derivative with respect to the density, you got something like proportional to the compressibility or proportional to the liquid bulk modulus. All right. So the advantage of just taking the correlation function and do the fitting is that you immediately get some physics of your model, right? For example, you know the quadratic coefficient here basically corresponding to the bulk modulus of a liquid. So now you have solid liquid coexistence, then you know what would be the elastic property of your liquid. So the other thing is that we still have two more parameters, right? So C0 is related to the bulk modulus of a liquid, then from this kernel, I can pull out this C4 factor and trying to complete the square of this C of K. So you end up with this C4 times something like K minus KC square, the whole thing square. So which is similar to the kernel we have seen in the phase field crystal. But doing that, basically what we are seeing is the system tends to have a minimized energy when the density wave has the wave number corresponding to Kc. So just do a simple manipulation. You see that the K2 squared is equal to the C2 divided by 2 times C4, right? So that's the wave number of the preferred density wave. So the length scale would be inverse of that. So C2, C4 also decide what's the lattice parameter or the lattice spacing. That would be the inverse of that and take the square root, right? Because this is K squared. And in addition, we know when the density wave is exactly the wave number equal to Kc, then that minimizes the quadratic energy, right? But now if you just plug in a density wave with the wave number slightly away from Kc and do the expansion, immediately you are going to see the energy increase with that delta K, which means how far away you deviate from Kc. So in a sense, what you are doing is saying that different lattice constant, you try that as an insight and plug it into this free energy. And that structure is not going to minimize the energy. Instead, you're going to get an increase in the free energy. So in the same way we talk about the liquid elasticity, now you just have a strain solid and plug it into the inside of a strain solid and plug it into this free energy. You also get the increase in the free energy. And from that calculation, you can get the bulk modulus of solid, right? So you are going to have something is proportional to a certain coefficient divided by 2 times the strain square. So that's the idea. If you carry out that calculation, which means you just expand this K. So if you assume K as Kc plus a small wave number variation and do the expansion, that's the prefactor you are getting here. So actually, those three numbers give us 3 physical properties. And of course, the lattice constant is something we expected. But all those 2 physical properties we are getting here are the bulk modulus of a liquid and the bulk modulus of a solid, respectively. Okay? All right. So with all those parameters, now we can do the calculation similar to what we have done for the phase field crystal, is that you can now assume the solid is a summation of the density wave of the principal reciprocal lattice factor, right? Something we have assumed similarly. And of course, we expect that the magnitude of those density waves is equal to Kc, that value. Then plug in there, you can do a direct integration to see what's the free energy look like. All right. So for example, if we take the principal reciprocal lattice factor to be like BCC lattices, right? Then if you do this integration and per volume, so that's the energy density, you are expecting to get those function proportional to the amplitude, square, cube, and force, etc., right? Because here, before the truncation, you just keep expanding the log term, so you are expecting the higher order term. So that energy is still keep. You have to include more and more term. But let's look at the physics about this Helmholtz free energy density, right? There's a coefficient delta B in front of the A squared. So delta B here is actually associated with 2 numbers. Those are the liquid bulk modulus and the solid bulk modulus, all right? So just write them out. So what you need to do is just plug in this n here and back to here and just finish the integration. You will see those coefficients coming out, and they are associated with 1 minus rho C naught, and also associated with this rho times C2 squared divided by C4. Okay, so that's how you end up. The prefactor is associated with the difference between the liquid and bulk modulus. Okay, those two things. But with this formula now, we got a better understanding of the physics of this kind of free energy functional. Because, for example, we know the liquid will become unstable if the delta B is less than 0, right? If delta B is less than 0, which means BL is less than the bulk modulus, right? The liquid bulk modulus is smaller than the solid bulk modulus. Then if delta B is less than 0, you are expecting the energy drops, right? Because delta F would be less than 0. So any amplitude occurring out of this liquid, if there is a structure, then it's a preferred structure because the energy drops is something negative, right? On the contrary, I mean, suppose the amplitude are small, so I don't have to worry about the higher order term, right? So for liquid, that would be the energy maxima if delta B is larger than 0, right? So immediately, something we can have this interpretation is we can rewrite this delta B, which is the difference between those two things, to rho S minus rho bar divided by rho S. And the rho S actually can derive that value basically will be the height of the first peak. So it's also a function of C0, C2, and C4. So you need to manipulate the algebra a little bit in order to see that the delta B can be rewritten in this form. And Cm basically is a height. So you can see the height should be a function of C0, C2, C4. So that's associated with this delta B, BL, which is 1 minus rho C0. And solid B is this one, the solid bulk modulus. All right. But now we can interpret what is delta B. So because before you are asking about how does the parameter in PFC is associated with density or associated with the temperature, right? Now you can see delta B has the meaning that how far away or how close it is, the mean density is to the spinodal density, right? So we can interpret the rho S bar, this number, as the effective spinodal density. If the density is lower than rho S, so this is bigger than 0, so you have a liquid as a stable state. But if rho bar now is bigger than rho S, right, you have more and more density, then you are expecting small perturbation will grow. So that will give you a solid state. Okay. So similarly, if we are expecting if there's a solid state and you want to know what's the amplitude is going to minimize this energy. But since so far, if we consider more and more terms from the log expansion, this calculation is not that easy to do. But in the limit that the amplitude is not that big, you can truncate this polynomial to the quartic order. So just by retaining the term up to here, you can do the similar minimization process to get an amplitude to this certain value. All right, so that's also has a relation relative to the spinodal density, right? Okay. So the final step is that we want to associate this delta B with temperature, right? Because we know this coefficient of the quadratic term in the PFC is associated with epsilon. And there we interpret epsilon as the feeling of the physical quantity of temperature, right? So how do we make that connection? Is that usually on the phase diagram, typically you will see a solidus line and liquidus line. They are roughly parallel and roughly linear with the change in temperature. So if that's the case, if the solidus line and liquidus line roughly change linearly with the temperature, then you are expecting the spinodal line is in between, right? So that is going to change with linearly with temperature as well. So if that is the case, you can rewrite B because you are expecting the spinodal temperature, the spinodal density is proportional to linearly with temperature. So you can rewrite that in terms of the temperature. So once you have done that, then you can convert everything. If you want to, you can rewrite whatever you are having here in terms of the PFC parameters. Then there you start to have feeling or the physical interpretation of the parameter epsilon there. Okay, so basically, there are many ways you can connect PFC parameters to the density functional theory. The idea is that you only have a very limited parameter in the PFC, right? But as you can see here, even the pair correlation function itself in the reciprocal space, there are so many degrees of freedom. In principle, there are infinite degrees of freedom, right? But so it is impossible for the PFC to capture all the physics, but depends on the physics you would like to include. Then you can say which parameter they are important in your material problem. Then you can select those parameters that's crucial, and you want the PFC actually to capture those terms. Then you can do a parameter fitting to determine what will be the proper phase field crystal parameter you should be using. Okay, so clearly here, compared to what I have shown you last week, we have shown you that the PFC can reproduce a realistic solid liquid interface. But in that case, we don't fit the C0 parameter, right? So all the information we are having there is basically first P. But there is a trade-off, right? Because even in that case, because we have so limited free parameters, so some idea just to show you, if you want to include more parameter in the phase field crystal, what you can do. For example, in the free energy, we only have this psi to the fourth power term, right? But you can also add in this like certain coefficient times the psi cube term. That is allowed. I mean, we still have the free energy up to the psi to the fourth power, but in that case, because for simplicity, we don't include the cubic term. But suppose you include cubic term in your free energy functional, then there's a parameter that you can also fit, right? So simply by doing that, you can maybe use that parameter to fit this C0 or something else. So, but I think the nice thing is that what I've shown you last week for the solid liquid interface is that just by one simple parameter, and that parameter epsilon will give us a very realistic solid liquid interface. But for more physical or important physics you want to incorporate in the phase field crystal, of course, you will need to include more term. Okay? So starting with Elder's paper, and in the end, you are expecting the free energy functional, all the coefficient, you will have this quadratic term, right? And you will have all sorts higher order term in power of n. That's from this rho log rho expansion. But now the C2, C4 information that we have here, basically we can write that in a very similar form as the phase field crystal. You see this Laplacian operating on Laplacian, right? There's a prefactor R4 is associated with the C4 and C2. So basically you can rewrite this kernel to give you a feeling or to convince yourself that it's actually would be really like the Swift-Hohenberg free energy functional. Okay, so of course that will give you a preferred length scale like periodicity of the lattice, and also for certain parameter you have the solid liquid coexistence. So here, just for your reference, I just listed here. Okay, and of course in the calculation we truncate to the quartic order, so we don't have to worry about high order term. But which means you are expecting the amplitude of your solid oscillation should not be very large, so that you can justify this truncation. Okay, so it is the way you can make connection to the density functional theory. Okay. The nice thing about this formalism is that you actually start with something physical, right? You do a measurement on the liquid structure factor or the correlation function, then you have all the parameters you can plug in here, right? Just by a simple fitting to get the C0, C2, C4. So everything here, all the coefficients are physical parameters, okay? Similarly, if you want to extend the discussion to binary alloy, what we have before is just a single material, like BCC iron, for example. But if you understand all this expansion of the density functional theory, now you can just simply extend the discussion to the binary alloy. So you're still expecting ideal term, like rho A log rho A minus delta rho A and rho B log rho B term. But for the correlation function, you are expecting to have the AA correlation, which for the pure material, that's what we did, right? And also the BB correlation and the AB correlation. So if you have all this information and just expand everything like what we have done before, or just write down what's the kernel that you would expect in a Fourier space, then if you want to have a real space version, you can convert that back to the Laplacian operator. Then you can have a binary alloy model to study, for example, like binary alloy solidification, things like that, okay? Okay, so here just copy paste from Professor Elder's paper. So this is the equation 15 in this paper. So that's a way you can start from the density functional theory. The next thing you do is just saying, you can redefine certain parameter, like because now you have a binary alloy, you can define what's the total density and what will be the fraction of the A and B alloy, right? So you can rewrite that into rho and C. So everything starts to look more and more like a binary phase field model. Of course, I mean, you have two parameters. So we are not going to the detail, but just with more simplification, that's the final free energy functional you will end up with for this binary PFC. But in short, what you are going to have here is something for the mean density. So lowercase n is the mean density. So you have everything very similar to the pure material PFC model, or to what we just discussed, right? You have this BL, BS, and this kernel will prefer some periodicity, and we just include everything to the quartic power. But you will also have some other term that characterize the deviation, like AB fraction. So those terms you can return to some certain order, right? So just for your reference, if you are interested in model a binary system with all the knowledge that I share with you, you can simply start with the density functional theory of two materials and carry out all the expansion. But I would suggest you to read through Professor Elder's paper if you are interested in modeling a binary alloy. Okay? So just one more comment on this PFC and classical density functional theory. So let me show you one final thing, because last time, so I will talk a little bit about my work on this PFC parameter determination, right? Because last time I showed you that the parameter in PFC, the epsilon, is associated with the liquid structure factor or the correlation function. But I think that's important, but we didn't really get into the detail. So let me just use this page to show quickly how to make that connection. Why epsilon has this relation, something divided by like S of K, and also divided by the C double prime K, right? Very quickly. All right. All right, so if we want to determine the PFC parameter epsilon, and so that we rediscover the proper solid-liquid interface properties, right? So we need at least to capture the quadratic behavior in the free energy functional. That's something we have done before, right? You are expecting this A squared term, and the coefficient is 1 over S of K. And there's orientation-dependent square gradient coefficient over here, no problem. And from the PFC, we did a little bit multi-scale analysis, and to end up with this kind of amplitude equation. A little bit complicated, but it's doable, right? So there's some efforts to end up with this kind of equation. And for a steady or a stable solid-liquid interface, we are basically searching a solution that the right-hand side equal to 0. All right. So for the BCC, you will have 12 equations because you have 12 reciprocal lattice vector, which means you have 12 amplitude. So if you really write all of them, there should be 12 of them. But each of them can be derived from certain free energy functional. So if you take the functional derivative with respect to the amplitude, you'll recover what happened on the right-hand side. So very quickly, without working out the cubic term and the quartic term, right? Because they are not important, because we try to fix what's happening here for at the quadratic order. So you can actually quite straightforward to see that just for example for the quadratic term, right? Without getting into the special gradient. This linear term, right? If I just sort of guess what's the free energy functional for f, so that I take a functional derivative, I will recover this term. So you must have like this minus 3 precise c squared plus 1 times A011 times its complex conjugate, right? And divide by 2. Okay, so very quickly, you know, the corresponding free energy to the quadratic order must have this coefficient. So summation here is sum from 1 to 12. You have all these 12 BCC principal reciprocal lattice vector. And for this square gradient term, right, in the energy, right, because here you have like a diffusion term. So in the free energy, that should be a square gradient term. And also because the prefactor here is 4 times the direction cosine square. So in free energy, there'll be only half of it. So that's 2. And of course, you will have all those cubic term and quartic term coming out, which I don't care because the physics I'm capturing is actually only concerned those 2 terms. So the PFC free energy must have this structure and times some coefficient, times some number, right? But since when we minimize, trying to get this amplitude equation, the amplitude across the solid liquid interface, that prefactor does not matter. But we know in order to have the proper dimension of energy, there must be some prefactor here. That's something we're going to talk about later. So there will be some constant times this kind of structure with high order term. But those are in terms of the amplitude equation. It's not the real amplitude of your density waves. But there is a simple relation. The real density wave, the real density is associated with AJ0 by this epsilon 1/2 power. And Z is a slope special parameter, right? Because we distinguish the underlying oscillating length scale and also the one that's much larger that associates with the density wave modulation. But when we do the derivation, there is no Z here, just epsilon to the 1/2 power, sorry, right? You plug in those back because we want to compare very top this relation and that relation. So very quickly, this AJ0 can be plugged in. So we can have AJ0 equal to epsilon to the minus 1/2 power times AJ. Square of that gives me this epsilon to the minus 1 power, right? Inverse of epsilon. And here, AJ0 again, you will have this epsilon to the minus 1/2 power in the denominator. And capital Z here, just plug in this epsilon to the 1/2 power Z. So when they cancel out, you take a square, you have this epsilon to the minus 2 power. So everything we start here because that's derived in the amplitude equation. It's not the real amplitude because in the density expansion, we just say the true density can be expanded in terms of epsilon to the 1/2 power. So here just to recover what's the real amplitude and what's the real dimension, lowercase z. And once you have done that, the ratio between the quadratic term and the square gradient term has to be the same as what we have here, right? And because later on we can fix what's this F0 just also by compare those 2 terms. But the ratio has to be the same. If the ratio are the same, then you are expecting the same behavior of this density wave decaying from the solid side to the liquid side. This has to be true. So 1/2 3 precise c squared minus 1 divided by epsilon to the minus 1 power divided by these things, right? So epsilon minus 1 divided by epsilon minus 2 power gives you epsilon here. And 1/2 divided by 2, you got a quarter here, right? Should be equal to 1 over s divided by the minus 1/2 thing, so which is inverse of that. You multiply inverse of that. So you have this relation has to be true. And that basically gives you what is this epsilon usually used in the PFC, right? You should divide by whatever the prefactor on the left to the other side. So now that's why you have this a in the denominator, and this because the minus I switch the order for this 1 and 3 precise c squared. So this is the expression I was showing you in the previous lectures, right? So that's how you fix the PFC parameter in order to rediscover the proper solid-liquid interface. Okay. All right, so that's something, that's the last thing I would like to do here, just to conclude everything for the solid-liquid interface. Then I will move on to talk about the elasticity. Yeah, but so here is a closure that you know in our paper how we get this relation, right? So, but just a comments that you will find that we don't have the proper C0, of course. We only fit what happened on the first peak, and because there's no more degree of freedom in the current PFC. But as I just said, if you want to include more properties, you just throw in more degree of freedom. Then if you have enough degree of freedom, then you probably can capture maybe to a certain degree realistic structure, realistic correlation function. Then you can have more physics implemented. Okay, let's move on to solid, right? Elasticity in the phase field crystal model. So once again, the problem is that we start with this phenomenological free energy functional. We can write down the corresponding evolution equation for per psi, right? It's going to drive the energy toward the minima. But whether this PFC can capture realistic response if we compress or expand the lattice spacing a little bit. So immediately you can see that if the lattice is subject to some expansion or compression, so locally you can see the wave number is going to be deviate from 1. So if the lattice spacing locally deviate from 1, so this Laplacian plus 1 squared kernel will not vanish, and that seems like it's going to give us something positive, because with this number greater than 0, then you have to integrate this positive number times per psi squared over 2 and do the integration. It's going to be always positive. So since like the elasticity naturally arises in the PFC, since any local lattice distortion will increase the free energy, right? And of course, what Elder had in the 2007 paper, you also have this kind of structure, right? You are fitting that with this kernel. So this kernel can be rewritten as something Laplacian minus, or because this is actually positive, because C2 and C4 have different signs. So you are recovering this Laplacian plus some positive number, the whole thing squared. So again, if there's a distortion in the lattice spacing, then you are expecting plugging here, you can see the free energy increase. So that's the concept, the quickest way why you are expecting the elasticity in the phase field crystal model. But in order to really understand or to quantitatively compare with real material, we will need to work out what's the mechanical response or how the energy changes with certain deformation. So let's consider maybe BCC solid and subject to a box strain. Okay. So we know the n sites for this BCC crystal, right, is some certain density plus some amplitude times all those cosine x, cosine y times plus this cosine x, cosine z, and plus cosine y, cosine z, right? But now, because I'm trying to, in this case, actually squeeze my BCC, right? So in each direction, and reduce the dimension by this 1 plus zeta vector, right? So for stress-free BCC, each side will be 2 square root 2 times pi, right? But if there's some squeezing, then the zeta is something positive. So A reduces from 2 square root 2 pi to 2 square root 2 pi divided by something bigger than 1. So if that's my system dimension, now you can see why the n size has 2 times this extra factor in the denominator. Because when x equal to that, right, to this number, the 1 plus zeta cancel out with that one, so it starts to repeat itself. Okay, so that's a setup. So that's the n size for stress solid. That's a boundary, that's a dimension you set up for your phase field crystal simulation. Then you plug in that back to the free energy functional, and that's only focused on this Laplacian plus 1 squared term. So the psi is being operated on by this Laplacian plus 1 squared kernel, but since now the wave number is not equal to 1, the magnitude is slightly bigger than 1. So every time you take the Laplacian, it's going to give you this 1 plus zeta divided by square root square plus this 1 plus zeta divided by square root square. So you have this 2 of them. So that's why you have this minus k squared is minus 1 plus zeta squared. So you expand this term, right? If I only focus on this term, you are going to have the leading order will be the minus 2 zeta, right? And then something, the whole thing squared. So you keep expanding, just keep the lowest order term. So the lowest order term will be like 4 zeta squared, but divided by 2. So you are expecting, without really working out this psi integral or psi square integral, at least you know the energy will have something extra that's proportional to the zeta square, right? And times something that's only associated with this psi square during the integration. But since due to the boundary condition we are setting up here, when we do this integral, we also change the boundary, right? So although we are confining the BCC in a smaller volume, but just carrying out this psi square integral is not going to change. I mean, the result will not change with zeta. But now you have something extra that's coming out, that's associated with zeta square, which is always positive. So in the end, you are expecting, because of this Box strain, the energy will be bigger by something proportional to the zeta squared. And if you really work out all the coefficient, then you just say, oh, this term proportional to 1/2 k zeta squared, and that k should be the bulk modulus. And to be more specific, it should be the free energy density. You should divide by the volume. Otherwise, this is going to change with 1. That's not right. So the only different or detail is that you should recalculate the free energy density when you evaluate the elastic constant. So here, just the concept. So if you really work out, for example, for the BCC, you can really get what's the C1111 or C1122 or C1212, and that's proportional. That will be proportional to if you have a stress-free BCC. First, you know what's the amplitude, right? So now you are getting all those elastic or the stiffness tensor. They are some number times that amplitude squared, basically. And for the Young's modulus, you can do that for hexagonal lattice or BCC, but still the same. You will see the Young's modulus also proportional to the amplitude square, and this column is the bulk modulus, and G is the shear modulus. And Poisson ratio for the 2D triangle lattice will be 1/3, right, etc. So there is an appendix in Liu's paper. There, basically, we work out a very general formula for people to obtain those elastic constant for certain structure, which I will talk about in later slides. Okay, but the concept is that in order to quantitatively determine the elastic moduli for certain structure, what you have to do basically is to evaluate the energy increase. And always the increase to the lowest order is proportional to the strength square, and the coefficient is associated with the elastic constant to the corresponding operation. All right. If you try to apply a shear to your solid, and the energy increase here, the prefactor is associated with the shear modulus. Okay. So for example, because to really have a feeling how to get all those numbers, right? Let's work out one example, or conceptually, let's work out one example. So for example, let's work out the Young's modulus for these 2D hexagonal lattices. So for a stress-free hexagonal lattice, right, that will look something like this. And you have seen for many times that in the PFC model, the smallest unit cell should have one side equal to 4 pi over square root of 3, the other side will be 4 pi, right? Something like this. And this is stress-free. So if we want to work out the Young's modulus, so the operation to get a Young's modulus is that if I'm applying a strain in the x direction, in this case, I'm stretching in the x direction, right? So the dimension is being expanded a little bit to become 1 plus epsilon xx, bigger than before. If I do that, due to the Young's modulus basically is the measure about if I am deforming my material in one direction, in x direction, there will be deformation, in this case, in the y direction, which will minimize the elastic energy of the system. So if I'm applying a strain in the x direction, and there will be a responsive strain associated in the y dimension. And the Poisson ratio basically is the ratio between this applied strain or the responsive strain and the applied strain. Okay. And since you can, as you might experience in daily life, is that if you are pulling something in one dimension, you are expecting a compression in the other dimension or in the other two dimensions. So there's always a negative sign to correct that opposite sign for these two strains. So Poisson ratio is defined like this. All right, so what do we want to do first? Of course, we know for a hexagon lattice, if we just string my lattice in this way, right? In the x direction, so here should be x, should be y, right? So if the dimension is being stretched by this, then that's the corresponding end size, like what I show you for BCC. So you can always check by plugging that as my x. So x is from 0 to a times this number. So in the x direction, you can see when x equal to 0, this gives me cosine 0, which means the starting of this oscillation. When the length reach to the other side like this, you plug this in, 1 plus epsilon cancel with this 1 of epsilon. And because A equilibrium have this root of 3 in the denominator, it's going to cancel out. So with this 4 pi divided by 2, you recover this 2 pi. So everything check out, you should have stress hexagons whose end sides should look like this. The calculation is straightforward, but could be a little bit tedious. You should plug in this end sides back to the free energy and carry out the integral. And since you have been doing this calculation in the phase diagram construction, right? So you can use the same symbolic calculation, but not just modify your end sides a little bit and plug in to do the main, symbolic calculation. You can get the free energy as what? The free energy now, of course, as usual, will depends on epsilon and per psi bar. But those two numbers we are not going to change, right? But will be also a function of those two numbers, right? And of course, the epsilon xx, the strain in the x direction is something that I fixed. I only want to see what's the response in the y direction. So once I have this free energy functional, I want to know how the y direction, how the strain in y direction should be that minimize the energy. I only have to minimize this energy with respect to epsilon yy. So you take derivative with respect to this variable and requesting that equal to 0. You will see there's a relation between this epsilon yy and my applied strain in the x direction. Okay? So in the linear elasticity, the strain is always small. So if epsilon xx is really, really small, I don't have to worry about the square term. And since this is small, which means it's much, much smaller than 1, I can do a binomial expansion, and the second term will be 1 minus 1/3 epsilon xx. So 1 and 1 cancel out. You are expecting the responsive strain in the y direction will be minus 1/3 of the applied strain in the x direction. You plug in here, you are expecting always for a triangle lattice due to a symmetry, even without a calculation, you are expecting this 1/3 coming out, okay? But that's not the final answer because in the beginning, we set a goal to work out the Young's modulus, but here we only work out the Poisson ratio. But we need this response in the y direction in order to carry out the proper integration in the x and y direction. But with this information, if you do this calculation, you plug it in, and in the end, a little bit manipulation, but now you know the free energy is the loss function and also a function of the amplitude as well. Then you can also ask the question, what would be A look like? So when we do the calculation for phase diagram before, you roughly have the memory that the amplitude has this relation, but there's no this minus 20 epsilon x, right? So now it's self-consistent. If there's no strain, the amplitude should be this expression without this the last term. But if you add this strain, now the amplitude is going to change a little bit. But you can see since epsilon is always a very small number, usually it's less than 1%. So even that will not change the amplitude much. It's pretty negligible. So you plug in that back here, you just calculate the energy density of your solid with a little bit manipulation. You are seeing that stretched solid, the free energy density, is equal to the 1 unstrained solid free energy density plus some extra term and higher order term. And that prefactor should be 1/2 the Young's modulus times the epsilon xx squared, right? So that's how you get this Young's modulus equal to 2 times this prefactor. That's A times the amplitude squared. Yeah, but that's somehow kind of, a lot of work just to get the elasticity out of PFC, right? Later I'm going to show you there's a general way also showing Liu's paper, but actually spot check in 2010's paper, they showed it much earlier. So later I'm going to show you the other way to actually get all those numbers easily without going through the integration, all right? Okay, but before we move on to that discussion, let me show you a note from Elder. All right, so for 2D hexagonal lattice, you can strain your solid differently, right? So the most left figure is the strain-free lattice. So that's just a reference. All the atoms are located at this equal triangular site. But you can apply a shear deformation. So you can see the atom on top is not aligned well, right? It actually have this slightly shift toward right. So you can deform your lattice in this way. You apply shear deformation and calculate the energy increase. Then you can get shear modulus. And you can also deform your lattice like in x and y direction. If you expand this by 1 plus zeta and reduce the dimension by 1 minus zeta, you apply this deviatoric deformation, and that will give you the C11 and the C22, or C1 and C22. Okay, so here is the way you implement the shear strain, right? So you can see the x coordinate changes with y. So that's how you when you go a little bit higher and higher, the atom was shifting a little bit toward right. So that will be your strain zeta here. And if you do the calculation, I just show you the final result. But you can refer to Elder's paper in 2002 and 2004 and to see how the calculation is done. So here you can get this prefactor, and that should be the shear modulus corresponding to one of the stiffness tensor, right? Like C12, C1212. And if you apply this deviatoric deformation, right, just like I described, you expand in the x direction by zeta and also reduce dimension in 1 by zeta. You can get the sum factor, and that's associated with C1111 and C1122. If you apply a bulk deformation, then you can get this 12A squared here. And the bulk modulus will be twice of that, right? So that's for triangular lattice. Oh, they don't have a bulk modulus here, but here you can have a bulk modulus. But the bulk modulus is associated with this C1111 plus C1122, etc. Okay? So that's just concept, but I'm going to use the amplitude equation to really nicely work out all those coefficients, but that will take some time. But right before that, let me show you something that you can already reproduce easily in your PFC simulation, okay? So what you can do is to set up a unit cell, like 2D hexagonal lattice or like BCC, anything, right? You can set up one unit cell of the desired lattice in mind. Then here I just do an example for like bulk strain. Here I think it's a compressive strain, I think. Depends. Okay. So you just compress each dimension to a certain degree and let your unit cell actually run into equilibrium. Then you measure the free energy. So at the bottom, here is the energy versus strain. So I start from 0, and let me double check that that's compressive or tensile strain really quick. That's a tensile strain. Let me see. No. My definition is that when epsilon is something negative more, then I have a larger dimension, right? So that's a tensile strain. So the sign is wrong. Okay, so if I really plot, that should be tensile strain should be on the other side. Other than that, I think it's correct. So let me quickly fix that. All right, so the horizontal is the strain. So positive, which means tensile strain, right? Yes, that's tensile strain, exactly. So of course, for the linear elasticity, and we are expecting when k equal to 1 or like 4 pi and 4 pi over square root of 3, that should be energy minima. But actually, the minima is somewhere very close to like 0.1% of strain, right? So if you carry out this calculation, you'll see what's going on here, right? And if you try something, okay, so the parameter I'm using here is epsilon equal to 0.1, and the percent bar is like minus 0.19. If you reduce epsilon, you will see that the minima is getting closer to 0. It's something we are expecting. And the reason is that for epsilon equal to 0.1, we still open up a band of unstable wave number. And the numerical simulation is actually involve more modes in the real solution, which means when you do a Fourier transform of this triangle lattice, you will not just see a one mode, you will see many modes, okay? So which means the higher order mode also contributes. So in contrast to our theoretical analysis, we only invoke one mode and plug into the calculation. There you will see Q is 1, which will minimize the energy. But now you will have more modes, which means the first mode still involve like 6 wave number, right? So you have 6 wave vectors. So the 6 will be the one aligning the x direction and all 60 degree apart. But you can expecting the next receivable lattice vector get excited. The one will be like aligning a 30 degree, and the length will be larger than 1. So which means if I pick a wave number in x direction with magnitude 1, and also 30, also the other one 60 degree, I add those two things up, right? The resultant wave vector can resonate with those 6 reciprocal lattice vectors. So you are expecting some other modes can be easily excited. So that's the case. Why? Because now you have a second mode or higher order mode. That's going to shift the wave number, which minimize the free energy a little bit. So the reason you are not seeing the energy minima located at 0, that shift is due to the higher order mode contribution. So when epsilon is reduced, you are using maybe epsilon equal to 0.01 or even something smaller. You will see the calculation will pretty much, the minima will be located at a zero strength, because in that case, the higher order mode, the magnitude reduces with epsilon. All right. And this is important. That the reason I'm showing you this is, for example, if you are interested in this ATG instability, right? And you are saying that if you are going to strain the solid, and the solid is in contact with the liquid, and the solid liquid interface is going to be unstable. The planar one is going to be unstable. But when you apply the strain or the stress, you have to know what's the stress-free state, right? And if the Q is not at 1, so if you just prepare your dimension as like multiples of 4 pi, you are thinking it's a stress-free. It's actually not, it's already stressed. So you have to really take care of the higher order contribution to properly set up what's your stress-free state. Then in that case, you can actually see with the new reference or the new or the true stress-free state corresponding to Q is roughly, I think it's 1.047 something. And that will be your stress-free state. Then you can stress your solid relative to that state, okay? But here, just to give you a feeling or to take this opportunity to show you that sometimes you really have to take consideration into this shift in wave number. Although it's really small, it's only like less than 0.2%. But for calculation like ADG, that's crucial, right? It's less than 1%, it's only 0.2%. But for calculation involve like stress-driven motion, even you are looking at how the dislocation is going to move, and you should know what's the stress-free state look like in your system. Okay? Mm-hmm. Smaller epsilon will move that minima towards 0, because smaller epsilon, the band of unstable wavelet is very less, and you are expecting the higher order mode, the amplitude is reducing as epsilon is also reducing, right? So the 1 mode approximation will be a very, very good approximation only when epsilon is very small, right? But 0.1 obviously is not that small enough. But actually, because we are plotting, we are resolving this 0.1%, right, strength. So if you really plotting like 1%, 2%, 3%, you are not going to see that difference. Yeah, but I think that's important, so that's why I'm showing you this simulation, right? So this is easy. You can do a bulk strain. You can also do a like for example, the Young's modulus. What you can do is that you can apply certain like 1% strain, and trying to set up your system in y dimension, different y dimensions. You are going to find this one specific response or adjustment in y that's minimized free energy. You can from there you can measure the ratio between the xy the strain in xy direction, and you should get something like 1/3. Right, so numerically, that's something you can do, okay? But that's something you should do. But I would like to talk about, in theory, you can get all this from this amplitude equation. But bear in mind, the amplitude equation here we have already assumed 1 mode, okay? So even after all this calculation, you will not get that kind of modification, like in simulation, the wave number shift. That's something you will not get. If you want to get that shift, you should add in the second mode and do the minimization process, and you can really get the very nice prediction about that shift. Okay. Okay, but still, I mean, for small epsilon, you can get really nice results from this amplitude equation. All right, so we are going to use the amplitude equation or to get you be more familiar with this approach, okay? But we're not going to use the whole the whole thing. just a certain crucial part that involve the elasticity. All right, so that should be the part involve the gradient. Okay, so how do we incorporate this or in the amplitude equation, right? So how would be the strain changing the density field, right? So even without doing anything, you can think of that if now we only consider solid, right? So we know in a pure solid without any strain, the Aj should be a constant everywhere. So the density wave will be just a simple summation of a plane wave. And it doesn't distinguish from point A to point B, point C. Everywhere is homogeneous, right? That's a solid. A is the order parameter in a solid should be a constant. But if there's a strain, then there will be a special variation of this Aj, right? Because you can think this Aj, you can separate that into its magnitude and also its phase. A is a complex number. But if the phase of A can change over space, so you are expecting this one would have a turn like exponential I phi. And phi can vary across a space. So I can combine that exponential I phi with this exponential IKR, right? So I can write this phi as what? I can always write this phi, for example, in terms of exponential I times delta k dot r, because that phase is going to be changing as a function of space. So if I write this exponential I phi in terms of exponential I delta k dot r, then since that phase will change in space, which means I'm expecting delta k will not be 0, will be something across the space. So which that would describe locally lattice distortion just using the phase of the amplitude. So that's a concept. But we're going to go through a detail here, right? So how we can associate with here, for example, is the strain or the displacement field of atoms in the amplitude equation, or how does that strain, what's the relation between this strain and also the phase of amplitude, okay? So I'm going to follow this 2010 paper, Spotcheck. It's a work by Spotcheck and Karma. It's a very nice detailed derivation and to associate with the displacement of atoms and also the information we can get from this amplitude, okay? All right. Okay, so you can understand the relation by the following, right? So let's say there is a displacement field U of atom, which means if U equal to 0, then there's no displacement of atom. But if there's a strain associated, which means some of the atom being displaced by a certain number, and we are using U of R to describe that displacement, okay? So here I'm just talk about the spatial variation. So I only talk about these parts, right? Phi bar, let's assume it's a solid, so everywhere is a constant. So this delta phi characterizes where is the local density peak and something like that. So let's say if there is an atom being displaced by vector U, then I'm expecting 0 displacement solid. If I'm finding atom at some certain position here, then this locally profile is going to be look like what I have done for this displaced atom. So which means I'm moving the atom from original R to U, but locally I look at that profile because it's just being the same atom displaced. That function should be exactly look like what hasn't been displaced. The shape locally should look like this, right? So which means I'm just comparing of the process that we displace the atom with the one without. And if you look locally, the shape, and they should be the same. At least that's our assumption, saying the deformation will not change the amplitude a lot. Okay? So what is the unstressed solid locally look like? That should be this function. And I'm putting this 0 as there's no strain associated with the solid. And This part basically can be described by also the amplitude is changing because this strain and also exponential ikj now is being displayed. So the position I put in here is r plus u. And in the amplitude equation, the amplitude modulation is always small, right? It only changing on the scale over the interface. So one of the approximation is just saying the amplitude itself does not change that much, right? Although especially displacement is usually small. So a good approximation is just saying the amplitude does not change, although there's a deformation associated to the solid. And the goal is to get the description for this solid with a displacement, right? So by doing that, what we are working out is actually by dividing this exponential ikj dot u to the other side, or by simply shifting this r plus u and trying to write a density field with strain, but now just if you give me a position r, what's the density field is going to look like, right? So for a solid with certain displacement, we are ending up with the amplitude, whatever you can assume is not going to be affected by this deformation. And that part is just the density wave. But with the displacement, it's going to, like what I just described, you are expecting a phase coming out of here. And that phase is a function of space, and you can interpret that as a displacement of your atom, okay? So that's basically what we are going to use for the following discussion. But just note that the stress solid, now the amplitude involve two things. One is the amplitude without any deformation, which from the stress-free solid. But you know, if there's a deformation, there's always an extra term exponential that's something associated with this displacement in your amplitude, right? That's quite natural. Okay, so that's the amplitude. So without deformation, you can see u equal to 0. This just goes back to 1. So aj equal just to aj naught. But with prescribed displacement, you are just using this extra factor. So one exercise you can do is to maybe prescribe some sort of shear displacement. So once you put u as a function of space, and you know what's the amplitude look like, and plugging back, right? This corresponding amplitude, everything times the corresponding density wave, sum all together, and to visualize that, you can immediately see whatever you put in for this displacement is going to show up in your plot. So you can do that exercise to convince yourself that displacement of atom can be written in terms of this exponential minus ik dot u term. So, but we care about is if there is kind of deformation or strain, how does that change the energy of the system? Because from that practice, we can figure out what's the elasticity or the elastic constant. So again, we go back to the lowest order expansion in the density functional theory, and also its corresponding amplitude expression, right? So that's the Ginzburg theory or the same thing. You start with PFC, you got the same structure. The prefactor, the ratio is going to be the same, but just look different. But you always have this kind of structure, right? And we know the elasticity or the elastic energy only comes in through this gradient term, right? Because the amplitude would be just aj0 times some exponential factor. But if you always have some other term has this a squared, a cubed, a force, imagine this exponential factor is going to cancel out. For example, for the quadratic order, right? You have this and this complex conjugate. So you will not see the effect from the deformation. from U, from the displacement field. So the only part that will pick up this special displacement of atoms will be from this gradient term. Okay, so the following just to work out what's this contribution. So you will need to work out a little bit the math. So we want to calculate this. So just to quick remind you what's this Kj hat. That's one of the principal reciprocative factor, but in this unit factor form. All right, but all this J index just specify which reciprocative factor we are talking about. But in the end, we are going to sum all of them, right? So just for each J, we are going to do the same calculation. And Aj is the density, the amplitude of that density waves. Okay, so we are going to work out that square gradient term. But it's always easy to manipulate this special derivative in terms of Einstein's summation convention. So I can always write, for example, there's an inner product, right? Of course, it's from this vector and the vector operator, the del operator. So this term can be written as summation L from 1 to 3, Kj, taking the L element, and also partial XL, right? So those two represent an inner product of those two things, and operate on Aj. So the Einstein summation convention basically saying whenever you are seeing a repeated index, you are going to sum L from 1 to 3. Okay, but note that J here is not about special dimension. J is the which reciprocative factor we are talking about. So when I see repeated J, I don't sum anything of it. All right. So just keep in mind that repeated index represents summation from 1 to 3, except every time you see a repeated J, don't do that. Okay. So this is going to help us to simplify the calculation quite a bit. The only thing you need to do is to plug in this Aj here, right? We know if there is a displacement of atoms, Aj contains the one part that's not associated with the displacement, and the displacement information is in this exponential ik.u term. But quickly, you can see I'm just taking Aj, the derivative with respect to XL, right? So I will have two terms. One is the special derivative with respect to A naught actually, right? And I don't take derivative for the second part. I have immediately picked out the second term is the taking derivative of the exponential part, but I don't take that on the Aj, right? So what I can do is to consider the k.u as a new variable. So I'm taking the exponential I something and take derivative with respect to that something. So that's going to give me this minus I. And once I do that, I take the special derivative of this k.u, the whole thing, right? Because that's my variable. So quickly, you will get this minus I in front. And as promised, you should have this k.u. So k.u, which is km, and take a special derivative. So you can also write that as like partial L and k and m together. But since k does not change over space, right? K for a specific reciprocative factor is just a 3 number. That doesn't change. That's why I pull this Kj out. But other than, so you can really easily to manipulate everything using this index and the Einstein summation convention. Then I'm talking actually require the information of this operation square, right? But from here, you immediately see you can take this one and its complex conjugate. When you multiply that, you don't see this factor coming, but you always see something like a real part and imaginary part. So the square will be the real part square, right? That's here. You see this kjl partial L A naught square, and also whatever the coefficient associated with this I. So that's kjm, and also there's a prefix kjl, so that's why there are 2k. And this partial LUM and A naught squared. All right, so just this algebra, but you can, that's the final result. One thing to note is that you are seeing this K with a hat. That's represent the unit factor. But when I take the whole phase, the derivative, the K here is not in the form of unit factor. It's the whole factor. All right. In generally, you can assume it's not unit factor. So that's why I don't have a hat over here. Okay. So there's a difference. So whenever you see a hat that's a unit factor, you don't see that just the factor itself. Okay. Let's digest the result a little bit. If U field is the displacement field, right? And the way we define the strain tensor is just saying how the displacement is going to change over space. So the strain tensor is defined as this kind of symmetric operation, right? So you have a displacement in certain direction, take a derivative with the other direction, and symmetrize that. Okay. So immediately you are seeing that contribution, because in the end we are calculating the energy contribution, right? That's a free energy, and we are going to see how the displacement is going to influence that energy. And we are working out this gradient term, but now I'm seeing that the strain field indeed is going to contribute here, has a form like something square. So pretty much I'm going to expect the increase in free energy will be proportional to the strain square in the end. Okay? Okay, so let's rewrite just this gradient term. So I have two contributions, right? One is here, so I rewrite everything back to this del operator. So you can have, for example, you see here is L appear in K hat and the partial L. So if I write back in terms of the factor form, that will be an inner product of those two things. And etc. All the time I'm seeing this repeated index M, which means I should have this K and U, the inner product. And it's being operated by this partial L, so I know there should be a gradient of that. And after I'm taking care of that, the repeated index L indicate the other inner product. But anyway, you are getting this form. So a little physics. So the first term does not associate with the deformation, right? And in fact, in previous calculation, we are calculating a solid-liquid interface. And by that time, we consider stress-free solid in contact with liquid, and we try to evaluate the density profile for this stress-free solid. So actually, this term is actually still describing that effect, right? It just tells you if the amplitude drop from solid to liquid, it's going to cost energy, right? Because it's going to evaluate how fast the amplitude is changing across to the liquid side, especially, right? So this term has nothing to do with the elasticity. Only the second term is associated with strain, right? Because we know we are seeing something here like the strain tensor is coming out of here. All right, so very quickly we can say if I only evaluate the contribution from this term, so I'm calling that free energy associated with this term, the elastic energy. So if I calculate only the elastic energy in the solid, so I'm doing this integration over space, right? So what I'm getting here is that if I'm doing something across space, if I divide by that, I get the energy density. It's going to have some prefactor. It's coming from here, right? So I can say the prefactor will be 1/2 rho naught kBt times this minus 1/2 C double prime. So I'm just writing everything out of here as this prefactor. And all these things square, right? I'm plugging back and doing this summation for all the residual lattice factor, right? Okay. So now the question is, so I'm putting those three things together to get the elastic energy contribution. Okay, that's right. You roughly see this 1/4 coming out. Right? It's 1/2 here, and minus retain. And C double prime is always negative, so there's no problem. Like this, this C is always something positive. So depends on what kind of operation we are acting on the solid, what kind of displacement or strain I'm giving, I will get some different prefactor, but always proportional to the strain square. So whatever operation I'm giving to the system, I can get either the shear modulus or the Broca modulus or Young's modulus, etc. Right? But I can get everything done just once for all. Okay, so here just one more step to take care of if the K here we are choosing is not the unit factor. So with the length actually equal to capital K here. So if I divide the K, capital K here, and again the square, I'm getting everything here is in form of K hat. That's it. All right. So the coefficient here involve product of reciprocal lattice factor. And I'm going to sum, for example, if j equal to 1, this will be K1, and you have to let me know the L is in which spatial dimension. So L, M, alpha, beta, all the possibilities from 1 to 3, because in 3-dimensional space, that's X, Y, Z. But each time, when I take one specific reciprocal lattice factor, I can get 4 numbers if the Lm alpha beta is specified. But this Lm alpha beta is actually in a special form of this string, right? If Lm equal to 1, 1, so this term is the string in the x direction. If alpha beta equals to 1, 1, so that's basically saying if I just string the solid in the x direction, and what's going to be the increase in free energy, things like that, right? Okay. And as you are expecting that in the PFC, the elasticity or the elastic coefficient will proportional to the amplitude square. So amplitude square is over here, very nicely. Okay, so just to give you a solid example, of course you are expecting the physics here is correct. And the linear elasticity naturally come out of this calculation, right? So one way to make a connection with this stiffness tensor is that the energy equal to 1/2 something times strength squared. So whatever in front should be my elastic moduli, right? So I just said, so everything aside from this epsilon squared and 1/2, that will be a C, K squared summation, all these products times A squared is the stiffness tensor. So just to work out that a little bit. So here I'm just saying similarly, because we start from that structure, everything coming out from this gradient operation. So if you do everything similarly, the only thing different will be the prefactor, right? As we know that the prefactor will be different. But other than that, everything is very similar. See? So if you work out that, the structure afterward is not going to change. So you still have something proportional to A squared. And also the important thing is that there'll be this product of K and sum over the 12th reciprocal lattice factor. So if you do that calculation, you will find out that the prefactor will be 4, and that's it. So let's take the BCC, for example. You immediately can calculate what's the C1111 and C1212 and C1122, etc. So for C1111, you are taking Lm alpha beta equal to 1, which means I'm only taking the x component of the reciprocal lattice factor, right? And sum is from 1 to 12. So you are expecting a non-zero product if all the K contains a non-zero x component, which means I have a 12 reciprocal lattice factor, but I should not get any contribution from 0, +1, +1, but I will have all 8 contribution, right, from this 110 or 101, and all this plus minus combination. So I have 8 contribution, right? But for each one, I only take the x component. So it is a unit factor of the reciprocal lattice factor. So each component is 1 over square root of 2 and 1 over square root of 2 and 0. So that to the 4th power will be 1 over square root of 2 to the 4th power. So if you work that out, it's going to give you 8a squared. So that's your C1111. For C1122, you can do the same thing. So you are getting this 1122. You are expecting that's only coming out from non-zero from this +1 plus minus 1, plus minus 1, 0, right? So you only have 4 contribution in other sense, right? So this will be 4a squared. And the same thing for 1, 2, 1, 2, because you always should have a non-zero, the x and the y component, so you can get that. So that's exactly what you are expecting from the PFC. So for PFC BCC, you are always expecting the same C12 and C44, right? So that's if you plug in all the parameter you are getting from the liquid structure factor, you are getting like a 45 gigapascal for C12 and C44. And for C11 will be twice of that, that'll be 90, right? And the 1 mode approximation always give you the same C12 and C44, but which in reality you are expecting something different. And one fix to that is to incorporate a higher order mode. That's going to break the symmetry, will give you different C12 and C44. But here, just for the simplest theory, that's something you will get. Okay. Compared with MD, the magnitude itself is not that far away, but just to preserve the symmetry from to a lowest order, that's something you are you will be getting from the PFC. Okay. So either from PFC or from the density functional theory using the amplitude expansion, you're always expecting the free energy can be rewritten as 1/2 the stiffness times the strain square, right? So you can rewrite that strain stress relation, rewrite that as 1/2 of the sigma epsilon. And in the amplitude equation, so in a sense, the free energy is a function of the amplitude and also the displacement or the strain. And since we know the system always going to bring the energy toward the minima, so we know I can also take a functional derivative with respect to the displacement, and I expecting the energy is being minimized. So if you carry out that operation, you are immediately recover the mechanical equilibrium equation. So the system tends to fulfill that requirement, right? You have a divergence of the stress should be 0 in 3 directions, should be always be 0. Okay, so I just show you are expecting the amplitude equation fulfill that behavior, and also the PFC should fulfill that behavior. All right. So just to complete the discussion, in order to obtain how the displacement field or the let's say the density field and also the amplitude field, how that changes with time, the dynamic equation. Because in previous lecture, I only show you equilibrium profile, right? I only obtain the amplitude equation for solid liquid at equilibrium. But quite generally, you can use the method by Zifang Huang, introduced in this 2008 PRL paper. The idea is that since the multi-scale expansion is just using the perturbative scheme, and you can simply assume psi has certain order plus higher order term, and higher order term are not important, and introducing the fast and slow spatial variable, and plugging that whatever in your free energy or the evolution equation. By forcefully doing that, right, you can get the free energy like this, just substituting that as insights back to the free energy and also to the evolution equation. But I want you to focus on the evolution equation, all right? So the mean density is this N of R, and the amplitude is this A. So you just forcefully plugging that back to the free energy functional and also take the functional derivative to get the evolution equation. You immediately see that the mean density is through a diffusion, but the amplitude is not a conserved parameter, right? So you just follow an Allen-Kahn equation. So which means for the phase of A also happen at a much faster time scale than the density field. So that's why you can expect that on the scale of density diffusion, the strain field almost at all the instant during the PFC simulation reach locally the mechanical equilibrium. All right. Having said that, if you are not really happy about this kind of time scale separation, if you want to really fine-tune like how fast the diffusion is happening and how fast the mechanical equilibrium is happening. There is a method called the modified phase field crystal. So the idea is that in the phase field crystal, it's a purely relaxation dynamics. You have this a partial percent partial t, only the first time derivative equal to the Laplacian operating on the chemical potential. So you are expecting there's only one time scale occurring there. If you want to have more degree freedom controlling the behavior, what you can do is to change that dynamic equation to a higher time derivative. So instead of only have a first time derivative of psi in the evolution equation, you can add in a second time derivative. So you have something like the psi over time, the second derivative plus certain combination of the first time derivative equal to the same Laplacian over the chemical potential. And there, by doing so, if you are interested in that approach, check out this modified phase field crystal model. And there's a detailed analysis how you can separate on this elastic mode and also the diffusive mode. I have done this ATG instability back in 2009, I think. And back then, I only used the very simple PFC model to model this ATG. And there, I have a solid liquid interface. And the interface is going to undulate, right? But by doing so, it actually requires mass diffusion happening on the interface. But in order to have this ATG, you are requesting that in the solid, right, the local mechanical equilibrium should be achieved at all times. So although I'm only using this very simple PFC, it seems to work out very well. I can actually quantitatively compare with the classic elastic theory with what I'm measuring in the PFC, the strain field. So at each instance, actually PFC, just by using the simplest PFC, the mechanical equilibrium is actually behaving nicely. So, but depends on the mechanical problem you are trying to tackle with. Sometimes you might need to really resolve these two different time scales, right? Okay, so just for your reference, there's something called a modified phase field crystal model. It's a work done by Professor Prof's group, so something that you can check out.